This time we're gonna be talking about our organic molecules, basically the four major types of molecules that make our body and their properties, and this is critical for the whole year because we're gonna be talking about the same molecules over and over again. So please, even if it takes you a little bit extra effort, you will need to really focus on this. As I go through this, I hope that you have your textbook available, and that you look in detail at the pictures that I'm going to show you in your textbook, looking for the type of things that I'm showing you. It can be very scary, but please, 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 just spend a few extra minutes now at the beginning of the year, this first week, and then it will be all very easygoing. So please, here we go. I'm going to divide this into two videos. The first video, we're going to address carbohydrates and lipids. And in the second video, we'll address the proteins and nucleic acids. All right? So break it up into two. Here we go. So we call macromolecules, macro, you know, is big. These are the big organic molecules that make most of our body. And there are basically just four types. And I call them the Fantastic Four because that's what life is all about. And as you know, carbohydrates, lipids, proteins, and nucleic acids. And you should be all familiar with this since this is material that we cover in freshman biology. On top of that, if you read the nutrition facts in the labels of products, like in my yogurt here, you can see the label facts, nutrition facts. They always have their fats that are lipids, carbohydrates, and they always have the protein content. So these are words that you should be totally familiar with. And of course, nucleic acids, you know them. So we are going to talk about these molecules, and first we need to introduce the concept that most of these molecules are modular. They are like Legos. Basically, you build these very large molecules by attaching pieces together, one on top of each other, joining them through bonds, usually covalent bonds, pretty much covalent bonds, to make a very large molecule of different types. Now, these individual components, we call them monomers. Mono means one. When you have all these individual components together, joined in a certain way through covalent bonds, you call this a polymer because it's made out of monomers. Now, the way you make these polymers, the way you join them, remember, anytime you have a bond, it's the electrons in the outer shell that they need to be reacting. So, to make these long molecules, we are going to be talking about two types of reaction. These are the monomers, the individual units that we are going to have. If you want to join them together and attach another one, you are going to have to form some type of bond there to synthesize, to make this molecule. So to build it, let's use the word synthesis. We are going to synthesize a new molecule. We are going to join monomers, but in order to join a monomer, notice that this one has a hydrogen here. This is the new monomer coming. I'm not giving you a detail of all the atoms that are here. I'm just giving you a detail of what this particular monomer, this one Lego piece, has attached in one end and at the other. Notice that you have an OH, a hydroxyl, and a hydrogen on the other end. And notice that this partially built polymer there also has a hydrogen there. Every reaction that you use to build to make something bigger is going to involve joining these two, but to join those two, the hydrogen and the OH are going to react and they're going to be removed. I'm going to form water, and that is going to allow to have enough free electrons there in the outer shell to make a covalent bond. So, in this case, this type of reaction that joins monomers together by removing a molecule of water, very conveniently, is called a dehydration synthesis, because dehydration means when you lose water. You lose water, you have dehydration. Another name that you might find it by which is condensation. think when you condense things, they get smaller. Think of condensed milk, condensed soup. They get smaller. And how do they get smaller? Because you are removing water from them. So this is the condensation, let's get it tangled up. Condensation reaction or dehydration synthesis is what allows you to form these polymers. Every time you join another one, you lose a molecule of water. Now, this is just not going to happen by itself. To build something, every time you build something, you're going to require energy. It takes me a lot of energy to put these Legos together to make a humongous tower. But in biological systems, in addition to energy to bring these molecules and join them, you are going to require energy. Energy and enzymes. So, looky, ready? Here is my enzyme that is going to allow for the formation of that polypeptide. Now, what happens if I have a nice polypeptide here? I had built a beautiful polypeptide, many monomers together, but now I want to break it. Remember, it takes a lot of energy to build this. So all that energy is stored here in these covalent bonds. That's the beauty of it. You store energy here. Now what do you want to do? I want to break it, because usually breaking it, I'm going to separate them back into monomers. Now it was really hard to build. To break it, I just hit it, and it's really easy to break a contraption. You all know that. So what's going to happen when you break it? It's totally the opposite of the beginning. The process of breaking down a large polymer is called digestion. And remember, before we remove water, we remove a hydrogen from one molecule and an OH from another. So now if we want to separate them, guess what we need to give them back so that they are whole? We are going to need to add a molecule of water so that we can add the hydrogen to one and the OH to the other. Just the total opposite of the previous reaction. Now, this is going to be a digestion, because when you digest, you break down things. You cleave off, you break one monomer at a time. You add the water is split into the hydrogen and hydroxyl, and you separate it. Now, two names, just like before. You can call it the digestion, or you can call it a hydrolysis. The word lysis means to break or to kill. Lysol kills bacteria. So water breaking, because you are adding water in order to help break that bond. So this is the hydrolysis reaction or digestion. Now, what did we need before? What do you think we are going to need to have here to catalyze this reaction? Yes, we are going to need an enzyme. And remember, when we put this together, we had to use energy. What happens now that we break them? Well, now that we break them, energy is being released from those bonds. So, requires enzymes, and energy is going to be released when you break this, because please remember that energy is stored in the bonds. So if I have a nice bond here, bonds are usually indicated by lines. You have this bond and you, do you hear the click? That's sound energy. When you break the bonds, energy is released. So, dehydration reaction joins monomers together. Hydrolysis separates them. And regardless of what, in both you are going to have energy, and enzymes are going to be involved. So let's start with carbohydrates, our first group here. Carbohydrates, if you look at any molecule of carbohydrate, it's always made out of three types of atoms: carbon, hydrogen, and oxygen. function of carbohydrates in our body, you all know this, is basically they are the biggest source of quick energy available. They can be used to store energy. That's a little known function that people tend to forget sometimes. And that is a molecule called glycogen. Glycogen. We store glycogen. We store extra sugar, extra carbohydrates in a molecule called glycogen, and you store it in your liver and muscles. You didn't know that. Carbohydrates also can be used as raw materials right here to build other molecules. Oh my, it's freezing. This is freezing. Uh-oh, we're gonna have to stop this. Carbohydrates are also used, let me find my gadget just collapsed and died. Carbohydrates are also used, no, doesn't want to work now. Carbohydrates are also, we're gonna have to go old-fashioned here. Carbohydrates are also used for raw materials to build other molecules. Think of cellulose is built out of carbohydrates. Chitin, the exoskeleton of insects, is built of carbohydrates. And structural materials, everything could be made of these carbohydrates. So, let's forget about my gadgets here. Sorry about that, threw me off a minute. Oh, it's working again. Here we go, ready? So, raw materials, you use them to build other things. Structural materials build your body, cellulose, chitin, for example. So, this is very confusing. You don't understand a thing I have said. So, let's go to the basics of carbohydrates. Here is a carbohydrate, and please look at your textbook. We are going to focus on the elements. You do this once, and you're going to get it forever. So please take the time to do it. This chart is in your textbook. Here you have the basic monomers, the basic units of carbohydrates. Some can have 3 carbons, 5 carbons, and you know this one, ribose, in your nucleic acids, or 6 carbons, like glucose, galactose, or fructose. You will not need to memorize this, but you need to be able to watch them, look at them, and understand them. It will make your life so much easier. Please believe me. So, let's look at the 6 carbon molecules here. Notice that if you look at the atoms, you have a chain of carbons here in the middle. All 3, glucose, galactose, and fructose. Each carbon is pretty much attached to either a hydrogen or a hydroxyl, an OH. HOH, HOH. If you look at these 3 molecules and you count the number of carbons and the number of hydrogens and everything, guess what formula you get? The same thing that you all know, C6, H12, O6. 6 carbons, 12 hydrogens, 6 oxygens. Now, what makes them different? Why do they have different names? Look at them, please. Look at them. If you compare glucose and galactose, notice HOH here, they are flipped in position in this one. That's the only difference, and just that basic difference makes it a different molecule. So they have the same elements, but it's just subtle differences in where the carbons and hydrogens and hydroxyls are located. So the most common molecule that you're going to use for carbohydrates is glucose. That's the basic. That's what comes out basically out of photosynthesis. So it's the basic to build everything in the living world. It's an amazing thought. Here is your basic glucose. Remember, we had discussed that in biology life occurs in water. So what happens when you put this molecule of glucose, that is a powder if you want to, in water? It doesn't maintain that form, that linear structure. What it's going to do is the molecule is going to bend over and reconnect. And this carbon is going to go around and connect to that carbon on the top, and it's going to make a molecule that is like a circle, a ring structure. And so from here, this is what you're gonna see glucose most of the time, and most 6-carbon sugars do the same thing. Now, looky, please. Here you have H's and OH's marked all over. The carbons are numbered. Here is 1 carbon. Notice that they don't put carbons. Every time you see a ring structure, this is just for the sake of clarity. If I make a ring structure like that, guess what it means that you have in these corners? That means that in each one of these corners you have a carbon. Got it? So when nothing is written, you have a carbon. Check out what's written there. That's an O. That corner has an oxygen. So carbon 1, 2, 3, 4, carbon 5, and carbon 6, there is an extra carbon out there attached. Please understand this basic structure. Now notice that every carbon has attached an H or an OH. Same thing there. Notice how conveniently that there is an OH and an H here, and an OH and an H here. Very convenient. So this is how you're gonna see glucose, and you are gonna be masters of drawing my glucose hexagon. That is always gonna represent glucose. So here is our glucose. Notice that that was an oxygen. So carbon 1, 2, 3, 4, 5. Our 6th carbon is up there. And here is again the critical concept. This molecule is so energetically rich because the bonds between the carbons, those are covalent bonds, that's where energy is stored. Remember my pencil? Bonds store energy. Now, carbohydrates are kind of funny, and scientists love to create new names. Instead of calling them just monomers, in the case of carbohydrates, they like to call them monosaccharides. Saccharose means sugar, so 1 sugar. So here we have, again, our beautiful glucose. That's the 1 monomer. That is 1 Lego. Now, what happens if I get 2 Legos together? 1 and 2. 2 Legos together. Now I have a disaccharide. Haha. Now, what happens if I put a bunch of Legos together? More than 2. Then I will have a polysaccharide. So 1 glucose together, or 2, or many, that's what these generic names mean. So we're going to look at a couple of them in more detail. So again, just to review, if you're going to build molecules, I'm going to skip the first one here. Going to the second one, same thing, you can do it slower. 2 carbohydrates there. This is glucose. This is fructose. They look very similar. The only difference is down here. Notice that here is kind of different. So I have 1 right there. Notice, notice, notice. I have 1, I'm gonna circle it, 1 monosaccharide, 1 monomer. And I have another one down here. Very nice. Got it? Guess what we are gonna do to join them, to make a disaccharide? We are gonna remove a molecule of water, and what we are gonna remove is the hydrogen of one and the OH of the other one, right there. When we remove that water, guess what you have left? We have just that oxygen. Remember, you remove an H and an OH, you only have that oxygen left to connect, and that is what you have there. Now this, what kind of reaction was this? Because we are losing water? Dehydration reaction, or dehydration synthesis, and is also known as condensation reaction. Now, what happens when you join a glucose and a fructose? Loss of water. By the way, fructose is the sugar that makes fruits sweet. Haha. When you join those two together, you get a new molecule, a disaccharide called sucrose. And this is actually what is stored in plants. Remember, we get the sucrose that we eat from sugar cane, and from sugar beets. So, the sugar that you're eating every day is really a disaccharide, 2 monomers. One monomer is glucose, the other one is fructose. Plants put it together and make a molecule called sucrose. Cool, huh? All right, and that's the same thing that you have in all the candy. Now, how do you make polysaccharides? Well, the same thing. Just keep on adding an extra, and you keep on going. Now, when you are talking about polysaccharides, the most common ones are starch and glycogen that we use for storage. Starch is used by plants, and basically what they do there is just a long chain of only glucose. And this is used by plants to store their sugar. And it's used by plants because the starch molecule takes less space than having all those individual ones together. Remember that you remove water, and when you remove water, you condense. In animals, we store some extra sugar in the form of a molecule called glycogen, and you are going to store it in your liver and muscles. And again, glycogen is just a long chain of glucose monomers. Another one that you have is cellulose, the cell wall of plants. Guess what cellulose is made out of? Hello, cellulose is made out of, again, the same thing as before, just glucose. Glucose, but you end up with 3 different molecules. How is that possible? Simple. The way the glucose molecules are connected is what makes these molecules different. You can connect them all like this, or you can connect them like that, or I can connect them, get fancy, and connect them like this. Same basic component, it just depends on how you organize it, you're going to end up with different molecules. So, notice here you have starch, glucose, created by the dehydration reaction. These molecules, I'm just showing you a tiny piece. There are thousands of glucose together to make starch. Right? Remember, starch is what you find in rice, in potatoes, corn has starch, any of those things. Wheat has starch. And cellulose is what we find in the cell wall of plants. Again, cellulose is also one glucose after another. Take a minute and compare these two and tell me what you notice different between starch and cellulose. Notice the position of these oxygens in the bonds. Notice the position of these oxygens in the bonds. All of them down, up and down, up and down. That's the only difference. That's the only difference. Do you need to remember this? No. So don't worry. But it's important that you understand this concept. Starch, easy to digest. With starchy foods, no problem, and it's easy to digest because we have the enzymes in our digestive system that break it down. What happens when you eat cellulose, the cell wall of plants? Every time you eat any plant material, you are eating cellulose. Lettuce, tomatoes, peppers, cucumbers, apples, pears, bananas, pineapples, watermelons, whatever. everything is plant material, has a cell wall. What happens to all that cellulose that is in the cell walls when you eat it? Oops. We do not have the enzymes to break it down. So all this cellulose that we eat, guess what? We eliminate it in our feces, in our poop. And this is what we call fiber in our diet. Cellulose that we cannot break down and we just pass it through. It's the same thing that this paper is made out of. I can eat paper, I can swallow it, and guess where am I gonna see it again? When I go to the bathroom next time, it will be there because I do not have the enzymes to digest it. However, what do cows and deer and all those herbivores eat? Grass, plants. So what does that mean? Do they have the enzymes to break down cellulose? Cellulose is the most abundant compound on Earth. Think of trees, plants, it's all cellulose. Herbivores do not have the enzymes, just like I don't and you don't. We don't have the enzymes to digest the cellulose, the cell wall of plants. Not at all. Not at all. It's undigestible roughage, or in more fancy terminology, fiber. So, how do herbivores get enough energy from eating just that cell walls in grass and nothing else? Well, they do not have the enzymes, but their bacteria in their digestive system, the bacteria, the lowly bacteria, are the ones that have the enzymes needed to break that bond in cellulose and release those individual molecules of glucose. How's that? Pretty cool. So, question. What happens if to this wonderful cow that is packed with bacteria, I give it some penicillin, some antibiotics that kill bacteria? Antibiotics kill bacteria. You know that, right? I give this cow antibiotics. What happens to it? Could be a cow, could be a rabbit, any of these herbivores that we have around. What happens to my cow if I give it antibiotics? Come on, think. It can keep on eating forever and ever, and it will die because it's going to starve to death because it does not have the bacteria to break down that cellulose to be able to use those glucose monomers for energy. So on the other end, the grass will come out exactly the same way that went in, totally unbroken, besides the chewing component. So think about it and meditate. Anytime that you eat carbohydrates, rice, wheat, any wheat product, corn, all those starches are made out of individual glucose molecules. Now, let me do something to show you here. This is starch, right? If I taste starch, how does a potato taste like? How does rice taste like? They don't taste like much, unless you put some spices on it. This doesn't taste like much. However, let's break it up. Let me cheat here. There you go. Let's break this starch into the monomers, into these glucose molecules. How does this glucose molecule, how does it taste? It tastes very sweet. So, when you taste the one molecule, or the two, mono or disaccharides, they taste sweet. When you are dealing with the polymer, when you are dealing with the starch, it doesn't taste like anything. Now, plants are going to store all the extra glucose in their cells. That's why we eat rice and that's why we eat potatoes, because they have a lot of this energy stored there. when you eat way too many carbohydrates and you have more than you need to use for power your body, guess what your body does with the extra carbohydrates that you have? All that extra glucose that you ate, your body puts it together into a molecule called glycogen and goes straight to your liver and straight to your muscles. And it's stored there, some of it. What if you have way too much more glucose, more than you can have to store in your liver and in your muscles as glycogen? What do you do with the extra glucose? It becomes fat. So, of all the glucose that we consume in the different forms, your body stores some as glycogen in your muscles and liver, and the rest goes all to fat. All right? So think about, those are your carbohydrates. Things to remember: monosaccharides, glucose is the most common. You put glucose together and you can make starch, glycogen, cellulose, chitin, and a number of other compounds. Good? Don't forget your dehydration reaction to make them and a hydrolysis to break them apart. Drill this, make drawings, do whatever you need until you get it right. Good? Excellent. So now that we are done with the carbohydrates and I kind of got you introduced to the fats, let's go to the lipids, our next group. These are much, well, I was going to say easier, but they're about the same. Fats are slightly different. You're all familiar with fats, and fats have very important functions in our body, and we need them. Most of us, we despise our fats, but we do need them big time. First, they allow us for long-term storage. If you don't eat for a week, guess what is powering you? Right here. Even if you don't eat for 12 hours, you're burning fat after a while. Long-term energy storage. Insulation. We have a layer of fat under our skin for insulation that allows you to maintain your heat inside and the cold outside, or vice versa. And we also have nice cushions of fat. Actually, your organs inside, around your heart, even though it looks terrible, you have a nice layer of fat around your heart, and it's normal. You have a little bit of fat around most of your organs, because when you move and do things like that, your organs are bouncing. So the fat kind of is like a bumper so that they don't get bruised. And you also have a nice layer of fat on top of your gluteus maximus, so when you sit down, you are not bruising your muscles all the time. And of course, when you have extra, more than what we need, if you are a female, it goes here and your thighs. If you are a boy, mostly it goes over here. So great fats. So let's talk about chemistry of fats. Most lipids, fats, are going to be composed, again, CHO, but very little oxygen this time. Ooh, very little oxygen. And unfortunately for fats, you need to remember the 3 different types that we are going to have. Regular stuff that we call fat. The real name for that fat that we call just fat is triglycerides. Okay, that's the real name. We'll get to it. Then we have phospholipids that you know from this membrane of the cells, and steroids. Those are the 3 types of fats that we need to know. So, they are kind of funny because they don't make these long molecules like putting monomers together. They are made out of fewer pieces, and they play different. So let's look at them. Number 1, fats. These are what we call our triglycerides. And these molecules are made out of, again, you have to join pieces, but the pieces that you join is 1 molecule of glycerol that is right here. Notice the structure has 3 carbons and HOHs. And then you attach to it fatty acids. You attach actually 3 fatty acids. This is a fatty acid. It's a different molecule. Notice, here you have a glycerol. Here you have a fatty acid. Please notice the glycerol has H's and OH's. Please look at what the fatty acids have. Please. A chain of carbons, and attached to every carbon you have a hydrogen. So if I'm a carbon, attached to every carbon you are going to have a hydrogen. Now recall, do you see any oxygen here? What kind of bonds are these? These are all just regular covalent bonds, non-polar, no charge, no charge. This molecule is hydrophobic, does not like water. So, through dehydration synthesis, guess what's going to happen? This fatty acid has an OH here. This OH is going to join with this H, and what is it going to make? The water. And the removal of that molecule of water is going to allow this to attach to the glycerol. Right there. Of course, what are you going to need? An enzyme. And so I said that these are called triglycerides. Here is your glycerol. And remember from before, how many places, how many, let's go one more, OH, OH, OH. Hello, you are going to attach one fatty acid here, another fatty acid here, and another fatty acid here. You can attach 3 fatty acids to that molecule. One fatty acid here, and that is where you lost the water, and you lost the water. And this is called a triglyceride, made out of one glycerol and 1, 2, 3 fatty acids through dehydration reaction. Go, 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 go. Ah, got stuck again. There you go. Let's do it again. It's kind of in slow motion, not working. Ready? Here we go. Ah, beautiful. Ready, set, go. One water coming out of there, one from there, one from there. Dehydration reaction. But you need an enzyme to help them to join. Beautiful. Now, remember I mentioned they are non-polar because it's carbon and hydrogen, beautifully balanced. If they are non-polar, they are hydrophobic, very good. They store energy because they cushion organs also and insulate the body. Did I mention before where was energy stored in any of these molecules? The energy is stored between the carbon bonds. How many carbons do you have here? How many bonds do you have here? My goodness, there is a ton of energy stored right here in these lipids. Alright? So these triglycerides, this kind of molecule is what stores energy, body fat, cushions organs, gluteus maximus, and insulates the body. Normal layer of fat under our skin to insulate ourselves. This is the fat that you have. Now these fats, unfortunately, and you heard of this, can be of 2 types, saturated and unsaturated. A saturated fat is what we have here. Notice every single carbon is attached to a hydrogen. If they are so packed with hydrogens that these poor carbons are pretty stiff, they cannot move. There is no way to move because there is hydrogen everywhere. This is called a saturated fat because it's saturated with hydrogens. They cannot move. They are stiff. They are solid. That's animal fat. When you eat a steak or something, that yellow thingy, that's solid fat. When you eat butter, That's solid fat. That means that that fat is made like this, with fatty acids that have hydrogens all over. The hydrogens is what makes you solid. So, every hydrogen attached to another one, nothing. So they are solid at room temperature. Animal fats are pretty much saturated fats. So any fat that you get from an animal is solid, is saturated. Think about it. Saturated fats, because they cannot move, they are very stiff, they are usually, or they're always solid at room temperature. Please, solid at room temperature. Very, very important. Let's look at unsaturated fats. What happens here, and unfortunately I don't have a model without the, if you look at this, what happens, looky, in your textbook you have models of this. What happens if I remove this hydrogen and I remove that hydrogen there? Well, then this bond here between the carbons has to be a double bond. Alright, so we have a nice double bond there, but we don't have hydrogen there, right? So what happens now that you have a hole there with this fat? If you are not packed with hydrogen, this fat now can bend. It can go, woo, woo, woo. It's liquidy. It can move, it's flexible. So unsaturated means that unsaturated, not saturated. All these unsaturated fats right there have double bonds of carbon because they are missing some hydrogens. And because they are missing some hydrogens, they can kink and they can move. You know, boys are very stiff for dancing. They are like saturated fats. Girls are much more flexible. So girls are like unsaturated fats. Where do you find unsaturated fats? Pretty much any fat of plant origin is unsaturated, has those kinks and makes it liquidy at room temperature. Always very important. Right? So these double bonds there allow you to be missing hydrogen, and that allows kinks so you can move. Those are your unsaturated fats. Please make a diagram, do whatever you need to, work on this, learn it. So we have our triglycerides, right? It's a glycerol with those fatty acids, and the fatty acids can be very stiff or can be very flexible. Got it? Good. Second group of fats. They are called phospholipids, and you are very familiar with them. A phospholipid, hello? Guess what it's made out of? A glycerol. That's not changing, glycerol or glycerol. Instead of 3 fatty acids, now we have 2 fatty acids attached. Ooh, but remember the glycerol had 1, 2, 3 places to attach things? Guess what is going to attach on the 3rd place? A molecule of phosphate, phosphorus. And that is going to give you what we call a phospholipid. So what is it going to look like? Little diagram. Here is your glycerol. 1 fatty acid, another fatty acid, and right there you're going to have your phosphorus. And that makes a phospholipid. You have a diagram here. 1 fatty acid, another fatty acid. Here is your glycerol. Notice your 3 carbons. Fatty acid, but attached to the 3rd one, instead of having a fatty acid, you have a phosphorus. And now phosphorus again. Let me introduce you to another big player in biology. Phosphorus is a phosphate, F, phosphorus, and surrounding it you have 4 oxygen molecules. And what do we know about oxygen? Electronegative, electron sucker. Can you tell me what the charge of this molecule is going to be? It's sucking electrons from everywhere. It's negatively charged. Ooh, so check it out. A phospholipid has this phosphate that has a lot of oxygen, so it's going to be charged somehow, a little bit, and has these fatty acids that are totally full of hydrogen and carbon, totally non-charged. So right here, you have a molecule with split personality. One part of the molecule is polar, is charged, and the other part of the molecule is non-polar, no charge. This is hydrophobic, and this is going to be hydrophilic. This part of the molecule is going to be attracted to water, and the other one is going to be totally repelled by water. So why is this so important? It is so important because our cell membranes are formed of what we call a phospholipid bilayer. If you recall the pictures of the membranes, you have the little circles, that is the phospho part, and those tails, that is the lipid part. Phospho, polar, lipid, there. And the 2 layers, if you notice, the lipid part is all in the middle, away from water. Where the phosphorus part, that is hydrophilic, is to the water outside and to the water inside the cell. Meditate on this. This is going to work as a barrier because the middle of the membrane is totally hydrophobic. No water here whatsoever. And this is where the water is. So there is a barrier. Things cannot go across around it. So beautiful system. Alright, quick review. So let's see how your brain is working. So if you have a fat that is solid at room temperature, what do we call those that are solid at room temperature? And remember, they are solid because they are full of hydrogen. They cannot move. They are like boys, stiff when dancing. They are saturated. If you are liquid at room temperature, means that you can move. That means that you are missing hydrogen. So you are unsaturated. Good? Saturated solid, same sound. Unsaturated liquid. Now, question. Which one of these will remain flexible or more flexible when it's cold, very cold? If you need a visual, think of a stick of butter. Think of a bottle of oil. You put it in a place cold. Imagine an animal in a cold place. Fishes in the Arctic. Temperature 34 degrees, very cold. Which of these 2 fats will remain flexible so that the membranes can be flexible and the creature can be flexible? Which one? Which one? Which one? Yes. Unsaturated will remain flexible when it's cold. Think of what happens to a butter of stick when you put it in the refrigerator. It becomes even harder. So this is going to be very important because creatures that live in colder places are going to have some more of these unsaturated lipids in their cell membranes. Now, opposite. What happens if you are in very hot areas? You live in the tropics all the time, or in the Middle East in the summer when it's 110 degrees all the time. Which of these 2 will allow you to keep your membrane more together without just melting away totally in the heat. Which one will provide a little bit more structure, a little bit more rigidity to the membrane? In this case, the saturated ones are going to be more important. So organisms that live in very hot places normally have a higher content of saturated fats in their membrane. Please think about it. It's unbelievable. It just works so beautifully. Triglycerides, regular fat, phospholipids, membranes. Type of lipid number 3. You need to know this one. It's the weirdest and it's totally different from the other one because you don't make it by joining things at all. Welcome to cholesterol. This third group is called, in general, steroids. And you heard of steroids. Steroids. A steroid is basically this structure. Remember that there are carbons attached to every corner with hydrogens, and that's not shown. So 4 rings of carbons. Cholesterol is a lipid because it's hydrophobic, just like the other ones. And basically you also have it in your membranes. It's found in your membranes. This is cholesterol. We hear a lot of bad stuff about cholesterol. High cholesterol is terrible, kills you, heart disease, all that stuff is good. However, there is a little thing. We do need cholesterol. We do need normal amounts of cholesterol. Because if you're a girl, you are producing estrogen in your ovaries. If you're a boy, you are producing testosterone in your testicles. Guess how your body makes estrogen and how your body makes testosterone. They need to start somewhere. And guess where your body starts? Starts with a molecule of cholesterol. It grabs the cholesterol and modifies these molecules, these little components here, just a tad. Replaces these things. And if you replace just a few of these, if you replace of this one, you can have estrogen or you can have testosterone by just replacing those small attachments there. The molecule remains the same. You replace the attachments in cholesterol and you end up with those things. So what if you are extremely skinny, you are a girl, extremely skinny, 0 body fat, you are an athlete, you know, a marathoner, no body fat whatsoever. Your body fat is minimum, is 0. Guess what? You don't get your periods probably. Because you don't have enough fat in your body to produce enough estrogen to have your periods. Same thing if you are a boy. Way too skinny, 0 body fat, no nothing. You probably have lower amounts of testosterone. Now, we are in a place where we know your body makes cholesterol, so that's not a problem. But if we suppress cholesterol, you are out of this too, because cholesterol is needed. And cholesterol, please, is a type of fat that we call steroids. Yes? So we have our triglycerides, a glycerol with 3 fatty acids. We have our phospholipids, a glycerol, fatty acid, phosphate. And then we have the odd one, the weird one, which are our steroids, of which cholesterol is the biggest example. And why is cholesterol so important? Because starting from cholesterol, you make estrogen and you make testosterone. And you need to visualize this cholesterol and remember that shape because it never changes. That's it. So, where do you find cholesterol? You find it in your cell membranes too. So you do need it in animal cell membranes. And in the cell membrane, it's going to contribute to maintain the flexibility of the membrane, just like the saturated and unsaturated fatty acids. So we'll stop here. The second part will cover proteins because there's a lot to know about them.